Okay, this is lecture 12, and we are currently working with two-dimensional electron gas system. So we have originally three-dimensional bulk material. However, by reducing the physical thickness of this bulk material into nanometer scale, then now this size quantization effect occurs. So that's the reason why, although our material is three-dimensional bulk material, but when it is placed in a very thin layer, then effectively it's behaving just like a two-dimensional electron gas. So originally, more exact term for this system would be quasi two-dimensional electron gas, because so this vertical motion is not perfectly prohibited. So previously we had a certain term like quasi, but nowadays it is more frequently called as just two-dimensional electron gas. Anyway, although we have the three-dimensional EK relation in our three-dimensional bulk system, but when we go to this thin structure, then our energy versus momentum relation should be changed. Previously we had energy which is a function of kx and ky and kz, but now in this two-dimensional electron gas description, the k vector is no longer three-dimensional one, so it should be regarded as kx and ky, because the motion is allowed along x direction or y direction. Z directional motion is not allowed, so it is not appropriate to consider momentum along the z direction. And still we have a degree of freedom along z direction. Then how can we understand this third degree of freedom? So in this two-dimensional electron gas description, in this case we introduce another quantum number, and this quantum number is corresponding to so-called subband. So quantum confinement effect due to this thin layer is reflected in this subband description. So for different subband, we have different wave function along z direction. For example, this can be possible example of our different subbands, and the motion along x direction or y direction, these motions are described as that of free electron. Okay, so this is just a qualitative description about our lecture content in lecture 11. Of course, we spend a lot of time to actual calculation. How can you calculate the total number of electrons inside the system? So maybe you remember it, but up to now I just qualitatively explain what is going in our lecture. Then we can expand our discussion to a little bit more complicated system. For example, think about a cross-section of our silicon channel. So it just looks like this. This is, once again, x direction, y direction, and z direction. And we have here yz plane, and for certain area this is silicon channel region. Then this is covered by another region, so which is made of, this one is now silicon dioxide, and assume that this structure is just expanded along the G direction. We have homogeneous cross section along X direction, and now our silicon is surrounded by the oxide layer, not only along this G direction but also along this Y direction. Then what will happen to our system? Previously we had E versus Kx and Ky and Kg. That was the three-dimensional system, but now we can easily understand here the only possible motion which is allowed is E versus Kx. So the information about the motion or wave function along X direction and Z direction, these information should be merged into a certain number corresponding to, again, Sau band. Okay, so in this case, now Sau band just to describe the motion or the shape of electronic wave function, not only along G direction but along Y direction. So we have to draw the wave function psi in YZ plane. So if we have to name this system, then how can you name it? Previously, when we have this Kg neglected, we called it as two-dimensional electron gas. Two-dimensional electron gas. So since in this system, two-dimensional confinement effects occur, then we are allowed to have one-dimensional free motion. So we will call it as one-dimensional electron gas. Is it really used or not? Yes, this term is actually used in our actual research development. Okay, so currently the semiconductor industry is facing a transition from two-dimensional electron gas to one-dimensional electron gas. It is only because previously people have made the structures like this. This is a silicon layer again, and it is covered by oxide layer, and let's say this layer is corresponding to our gate material. In this case, our electron occurs in this black position. So electron can occur in this position. So motion along this direction or that direction is not allowed any longer. The only free motion is just vertical motion, which is vertical to your monitor surface. So it can move to you or away from you. So already our system is one-dimensional electron gas. And more significantly, now we wanted to make a transition from this structure to that structure. If we consider this structure, then electrons will once again appear only this position, and also free motion is allowed only along this x direction. So the confinement effect will be even severe in this case, and we will have a full 1D electron gas. So this is the progress of technology currently appearing now. During the last few minutes, I just explained the change of transistor structures from FinFET to gate-all-around structure or nanosheet structures. So up to now, we have calculated the N total. So this one is a scalar number, so it does not depend on position. This is just a number. But now we wanted to calculate the electron density. So electron density means that for given position, which is described by x position, y position, and z position, then how many electrons are nearby there? That is the question. So why do we need to understand this electron density? Not only the total number of electrons. It is because once we understand this electron density, then it can be used as the source term in Poisson equation. So it can generate once again electrostatic potential as a function of x, y, and z. So that will be our eventual goal. So now anyhow we can understand N total, and this N total is actually have a certain relation with the electron density. So how can you find this relation? When we integrate this N of x, y, z to dx, dy, dz, the entire volume integration will give you the total number n. Since this is just number per cubic centimeter, and when we take this triple integral over each length scale, then this cube of centimeter, that is gone, and we will have just a number. Okay, so N total itself is quite much related with the electron density N, but that does not necessarily mean that when you know N total, you have full knowledge on the electron density. So today we will talk about how can we solve this problem. How can we calculate the electron density from given information about our solvent structure? We assume that we know the solvent structure. When we say the solvent structure, it is eigen value, okay, eigenenergy, but also it means that we understand the eigen function. The wave function is known to us. So by using this information, please try to reconstruct the electron density. So simple rule is, if we have a certain eigenmode, then the probability density to find that electron at certain position is given by the square of absolute value of our wave function. So you know it quite well. So this is the interpretation of wave function. This is a wave function as the probability density in the spatial coordinate. So when we represent it as a function of position, of course, you can project not only in this x, y, z coordinate, but you can introduce many different ways to project your wave function. However, in this course, we will just use the simplest one, this position dependent projection. So in this case, it is clear that, oh, since our wave function gives a certain probability density function to find out our electron, then this one will be related with electron density significantly. That is quite a natural consequence. But before starting our discussion in that direction, we first of all achieve this description. PDF probability density function like description. So in order to allow this kind of interpretation, then our wave function should be normalized. The wave function should be normalized to the volume, total volume integral of our square of psi dx, dy, dg should be 1. This is the required condition to interpret our wave function as a probability density function. For two-dimensional electron gas, we can have this wave function. So in general, we can have a much complicated structure, but since we are working with a two-dimensional electron gas, then we have a x-directional plane wave, y-directional plane wave, and also z-directional confined state. So think about this one. If you have one-dimensional electron gas, then how does it look like? It will just look like this way: k, x, comma, n, and it will be x, y, the function of x, y, z, and it will have another leading coefficient here, and we'll have just e to the I k x x and confined structure on y z, and it will have a certain quantum number n that will be a function of y and z. This is 2D electron gas. We have plane waves along x direction and y direction, and in 1D electron gas we have only x directional plane wave, and for y direction and z direction we have just a confined state, and they are all merged into subband index n. The next procedure is quite simple. By applying this two-dimensional electron gas wave function into our normalization condition, then you can easily understand this plane wave just simply gives you 1, and plane wave just simply gives you 1. So the absolute square of absolute of psi just given by a square, and also psi g square. Here psi g is z directional wave function, so which is corresponding to just 5 nanometer thick or just nanometer thick structure, and we have to integrate it, triple integrate it over our XYZ structure. But you know that this psi sub z, the z directional wave function, is a function of z only. So x directional over y directional integration gives you just Lx and Ly, and the remaining thing is just here. The remaining thing is just here we have absolute square of a and integration of g directional wave function over g direction. That should be 1. This is the required condition to interpret the wave function as a PDF function. Okay, then I think that I just repeat, or I just show you how can we obtain this normalization condition shown in the slide. So this is the reason why we have this condition. Up to now, we have done it without any further assumption, and here we have introduced that, okay, this is g directional, so g directional wave function itself is normalized also to unity. So integration of our absolute scale of g directional psi gives also unity. If we adopt this convention, then we can easily understand Lx, Ly, and absolute scale of A should be 1. So in order to satisfy our normalization condition, then now we have to have absolute square of A should be 1 over Lx and Ly. That is quite simple. So, so now each state contribute this contribution. If we have only one single state fully occupied, then that will be actually the electron density. This will be X, Y, Z. If we have only one electron, which is one state which is fully occupied, then this will be the electron density. Here you can see that there is actually no dependence on X and no dependence on Y. This one is just dependent on only Z direction. Okay, but say that we have two states fully occupied by this way, then we will have just twice larger electron density. Our electron density will be twice. And say that although we have two copies of this state, but each of them has the Fermi-Dirac function which is corresponding to just half. Then what will happen? We have two degenerate states. Yes, there are two states. However, each of them is just half filled and half empty. Then effectively it is corresponding to one fully occupied state, so we will have this function. So from our previous from our discussion, it is now clear that if we have a certain wave function, and if we have a certain Fermi-Dirac distribution corresponding to its energy, then the electron density, which is originated from these two information, will be just psi square times fd E. So of course, if we just specify psi sub z, in this case we will have Lx, Ly. Okay, this is the contribution from one single state. So if we have further states, then of course we have to introduce a summation over those states. So let's say we have introduced different subband index n, then we will have n, and E sub n is introduced to distinguish them. Okay, up to now I just explained how can we calculate the electron density from given information for the wave function and eigenenergy. So if we are considering one-dimensional electron gas, then we have to solve a two-dimensional Schrödinger equation. But right now we are considering just a two-dimensional electron gas inside the double gate structure. So that's the reason why we are considering the only g-directional confinement. When we consider 1D electron gas, we have to solve a two-dimensional Schrödinger equation, and solving Schrödinger equation in two-dimensional space is just a natural extension to two-dimensional real space. So that's not that difficult in principle, but you know that since we have a two-dimensional domain for Schrödinger equation, it becomes more expensive to calculate the solution. Previously, we had just one-dimensional structure, so numerically solving the Schrödinger equation for one-dimensional structure, that will be quite easy. However, if we go to expand our consideration to two-dimensional real space, then calculation of a subband structure will be quite time-consuming. One-dimensional infinite potential well problem. Oh, why do we consider this one? This one will be used as just a simplistic example we can achieve. So later we will talk about more general cases, but why don't you just apply our developed technique to 1D infinite potential well problem. In this case, fortunately, we have full knowledge on the wave function. Oh, this is the wave function, and since we are assuming that even g-directional wave function is normalized to unity, then we have to decide our leading coefficient here to satisfy this normalization condition. So you can easily find that this is the coefficient which satisfies this normalization condition. So when a state inside 1D infinite potential well is fully occupied, then the contribution to the electron density is simply given by, previously we have 1 over Lx and Ly, and square of our wave function, g-directional wave function. And this g-directional wave functions, its square is given by this number, 2 over Lz and sine square of n pi Lg. I wanted to stress that if we have different n values, n1, N2, and something. If we have different n values, then it will show quite much different shape along z direction. So if we have just one n equal to 1 case, then we will have this form. There will be no vanishing electron density inside this term. But when you consider the contribution from n equal to, then of course we will have something like this. If we have number 3, then we will have 1, 2, 3. So depending on which solvent is dominantly occupied, then your electron density will show quite much different behavior. Think about this one. Let's say we have a case like this. Our infinite potential wire. So this is infinite energy. This vertical axis is corresponding to energy. And here we have 0 electron volt. So happen to be we have a 0 electron volt. And let's say our Fermi level is located far below than 0 electron volt. Yes, say this is EF. Then what will happen? In this case, you can easily understand the observed electron density will be quite small. Why? Because our Fermi-Dirac distribution will be very small. But anyhow, when we draw it, then we can find that, yeah, this is only dominated by what? Dominated by n equal 1, the ground state. But if we increase our Fermi energy level here, then what will happen? Then still n equal to 1 is dominant, but we can find another contribution from n equal 2. And if we go or push our Fermi level even above above 0 electron volt, then certainly not only n equal 1 or n equal 2 or all other states below the Fermi level will be almost fully occupied. So we will have not this shape, but we will have more and more uniformly distributed electron density along this z directional coordinate. Okay. So MATLAB example is provided, so you can follow it. This page is just preparing some constant, and this is the actual calculation. Since we have multiple, how can I say, multiple eigen values or eigen functions, so we have to learn a loop. This loop for different subbands. So we have different subbands. Already we have done it before, but the point is in this time, not only calculating the n total, we are now calculating the electron density x, y, z. So please have a look at this electron density. This electron density is defined as a vector whose size is determined by nz, which is number of real space positions, so z directional position. And you can find that here this is just 2 over Lx, Ly, Lz, and here we have square sign of our wave function. N times subband number. This subband number is corresponding to integrated Fermi-Dirac function over our energy. So of course, not just integrated. Here we have used the density of state already. So that's the reason why we don't care about different k values. Okay. So this is the way to calculate the electron density. When we draw the electron density as a function of real space position, then you can find this curve. Of course, as I told you before, if we change the Fermi level, then when Fermi level is far below than 0 electron volt, you will find the electron density which is dominated by your ground state n equal to 1. And if you increase the Fermi level over the 0 electron volt, then you will find that there will be many different solvents contributing to your electron density. The shape will look quite different than this. Okay. Then up to now, we have applied our discussion to infinite potential well. So infinite potential well is analytically available. The solution of the infinite potential well is analytically available, but eventually we have to consider the more general cases. So that's the reason why this slide is prepared. So, we are now considering the electrons in silicon conduction band. In the silicon conduction bands. So therefore, when we talk about the potential energy term, which has been neglected up to now, we have to find out the conduction band minimum energy of our system. Okay, so we have to find out EC, but you know that in our convention, finding EC is quite easy because by multiplying minus Q to electrostatic potential, now you can point out the intrinsic Fermi level of your reference material. So your reference material would be just silicon, I guess. And by adding certain energetic difference between conduction band minimum and intrinsic Fermi level, this is just a given constant. Then by using these two terms, EI itself and difference between EC and EI, you can reconstruct the position, energetic position of your conduction band minimum, and you will use it as the potential energy term because you are now talking about the electrons in the silicon conduction band. When you think about this potential energy expression, since this is a given constant, so the only dynamic quantity will be this electrostatic potential. So once we understand electrostatic potential, then we can calculate the potential energy, and when potential energy is given, we can solve the Schrödinger equation. Then for this solution of Schrödinger equation, eigenenergy and eigenfunction, the wave function, we can calculate electron density. Then this electron density can be used to recalculate electrostatic potential. You can easily understand there will be also another loop to get the self-consistency. So as usual. So this is the Schrödinger equation we have to solve for two-dimensional electron gas. We have to solve this one-dimensional Schrödinger equation. And here we have second order derivation, and previously we had no terms related with the potential because that was just the infinite potential wave problem. However, now we have it. Oh, here we have potential energy term, and you can easily remember that this is given by minus q phi plus ec minus ei. You know it. Yeah. So for given profile of electrostatic potential, then you can find this potential energy term for given position. Then let's do the discretization. So you can do it quite easily. Since here we have second order derivatives, then it can be discretized as here. So psi I plus 1 minus 2 times psi I plus psi I minus 1. So I hope that you remember this from your previous lectures. Then by just applying this into here, you can find the final discretized form. Of course, here we have square of delta G, but that is multiplied to the left hand side and right hand side. So for example, here the original form has no terms like square of delta G, but now you can find it here because we have multiplied square of delta G to both sides. So now I think this is just a repetition of my previous explanation. So in order to calculate the wave function and eigenenergy, we need potential. So in order to start all of this calculation, anyhow we need a potential. So although this is not perfect one, but we will use just semi-classical nonlinear Poisson equation we have studied up to now. So although it does not have any quantum mechanical information inside it, but anyway, for certain special cases, it will be a good starting point. So just to believe it. So we will use this electrostatic potential, and by fixing the electrostatic potential as a given profile, then we can solve Schrödinger equation and get the solution. And from these two information, you can calculate electron density. How did you calculate the electron density? For given solvent, just to calculate Lg square and 1 over Lx and Ly, and Fermi-Dirac distribution by using also solvent energy. So that will be the contribution from one single solvent. Of course, you have to make a summation over different solvents. So by performing this summation, you will get the electron density, and this electron density will be used later to update your electrostatic potential. In order to um, validate our old discussion, we have to keep in mind that our g-directional wave function should be normalized in this way. This is the basic assumption to validate our interpretation of a wave function as a PDF function. Previously, when we consider infinite potential well, problem, we had the analytic solution, so it was quite straightforward to satisfy this normalization condition. But unfortunately, if we solve the general Schrödinger equation with numerical means, then there is no guarantee that your numerical solution automatically satisfy this condition. Okay, so in this case, how can you do that? In that case, you should manually calculate the coefficient, and you have to scale your wave function to fit this, to satisfy this normalization condition. So it means that, let's say you have a certain psi z calculated from your own condition or your own simulation. Now you have it, and you have to check whether this one equal to 1 or not. Let's say that when you evaluate it, happen to be your number is just 100. Oh, then what should you do? Then you have to scale your original numerically calculated wave function and just to multiply 1 over square root of 100. Then by setting this scaled version, then when you once again evaluate this normalization condition, then you will find that eventually you will have number 1. Okay, so this is quite simple, but some of you are confused. Some of you may be confused by multiplying 100 or dividing 100 or taking square root or just to keep the 100. So if you have a certain unscaled version, then first try to evaluate it. Of course, in general cases, you will fail to satisfy. So there will be certain number c. Then please multiply just 1 over square root c to scale your numerical solution. Then this scaled version will automatically satisfy the integral of the normalization condition. And then now our focus is how can we numerically integrate this left hand side. So it is quite simple. Here we have dz, but that is just interpreted as delta z, and make a sum starting from I equal to 1 to I equal to n sub z, the number of g directional positions, and just have psi g comma n, and its i's value. Yeah, so that is the discretized form of this integral. And you can say, you can say when I equal to 1 or when I equal to n sub z, actually this delta z is not a valid expression. In this case, we have to have just a half of delta z and half of delta z. You are right. I mean that this one is not perfectly correct. So in order to make it more uh, accurately, then we have to have half of delta G multiplied by psi G n 1 and square, and starting from I equal to 2 to nz minus 1 for all bulk nodes, we can just use delta G, and here we have psi G n I square, and finally here delta G over 2 and psi Z n sub Z square equal to 1. That will be the most correct expression for our integration. But point is, due to our boundary condition for Schrödinger equation, we assume that this one is corresponding to the interface node, and this one is also corresponding to the interface node, so they are assumed to be 0. So more accurately, this integration can be written as starting from number 2 and nz minus 1. Then that will be perfect. But anyway, in general, when you perform any kind of integration, please keep in mind that for bulk nodes, you have delta G as a control volume of each discretized point, but your interface nodes, which is corresponding to the boundaries, have just half and half length scale than the bulk nodes. Okay. Fortunately, we have covered most of our intended lecture contents. Then maybe I think that this would be the final one. Okay. So up to now, we have talked about the contribution of a single subband to the electron density, and I told you that by summing them all for different subbands, we can get the solution or get the electron density. But you know that we have not only one single valley, but we have 6 valleys with different mass tensors. So in order to actually calculate the electron density in realistic silicon conduction band, we have to consider 6 different valleys. So since it has different g-directional masses here, therefore you have to recalculate these quantities in many times. Actually, here we have, although we have 6 valleys, already each of them, or we can find 3 pairs. Okay, so our calculation is reduced to just 3 times from 6 times, and also these 2 valley pairs can be merged because they share the same g-directional mass. However, anyway, you have to calculate at least twice with heavy mass and light mass. Okay, so then my final caution is, don't skip the spin degeneracy. Spin degeneracy is nothing related with this valley degeneracy. So in addition to these 6 valleys, finally you have to multiply number 2 to consider the spin degeneracy. Okay, so let me just wrap up today's lecture with homework number 12. Okay, you have plenty of time to the next homework due next Monday, and please directly start from your homework number 8. Homework number 8 is just non-linear Poisson equation solver for double gate structure. It was not the entire MOSFET, but it was just a MOS structure. So that was just a one-dimensional structure. And you have already calculated the potential and electron density for different gate voltages from 0 volt up to 1 volt. So that is already done in your homework number 8. So for each gate voltage, first solve the nonlinear Poisson equation. It is already done in your homework number 8. And by using the already calculated electrostatic potential and consider it as a given profile, then calculate the electron density. You can just calculate n of x, y, z. Of course, x and y dependency is not existing, so you can calculate n of z. Please keep in mind that you have to consider 6 values and spin degeneracy. Then for each gate voltage, for example, Vg equal to 0, 0 0.1, 0 0.2 up to 1.0 volt, draw the electron densities and compare it with your semi-classical one. So you have already the solution from the nonlinear Poisson equation and compare your electron density calculated from your Schrödinger equation, and your comparison will give you very interesting result. In homework number 12, you don't have to try to get the self-consistent solution. You can just one-shot calculation for electron density. Just to treat your electrostatic potential as a given fixed profile. Then just to solve Schrödinger equation, and from the calculated subband structure, just to try to calculate electron density only. Okay, so thank you for your attention today, and see you next Monday. Bye.